Hey everyone, so welcome to my first lecture on ordinary differential equation. This will be a series of lectures on differential equations. So those who want to know the flow that I'm going to follow, then they can refer this book by Erwin Krejcik on engineering mathematics. Well, for the concepts, I'll be taking plenty of help from the online resources, but only those who want to know the flow that I'm going to follow, they can refer this book. Okay, so without wasting any times, let's start today's lecture. So today we are going to discuss the following topics: what are differential equations, then we will see examples, order, degree and solution of a differential equation. So let's start. So what are differential equations? Well, if I want to say in a very simple language, then differential equations are nothing but they're equations that involves derivatives. So till now we have seen equations involving variables, say x, y and z and so on. Now we are going to see equations that involves derivatives. Then such equations are called as differential equations. Now there are specifically two types of differential equations that one will encounter. So the one is ordinary differential equation, that is the theme of this playlist or this course, and the second type of differential equations are on partial differential equations. Those who are interested in learning partial differential equations, for them I have already made a videos on PDEs. I will post the link in the description. Those who want, they can visit that page or visit that video. Okay, so now what are ODEs and PDEs? So let me give you the brief idea about both the things so that you know what you are studying, right? So I usually give this diagram to my students so that keeping this diagram in mind is much more easier. So it's a differential equation definition, and then I say ODEs and PDEs. So what are ODE? So here in ODE, the main thing is you have only one independent variable, which we usually call x, and one dependent variable which we call as y. So here my y is depending on x, and since y depends on x, therefore dy by dx makes sense. And once I have dy by dx, I can talk about d2y upon dx square, d3y upon dx cube and so on. So all these are called as ordinary derivatives. So therefore if you have an equation that involves these ordinary derivatives, then such equations are called as ordinary differential equation. That's how this name came into picture, because it involves ordinary derivatives. Now what are partial differential equations? The equation that involves partial derivatives. Now what do you mean by partial derivatives? When does partial derivatives comes into picture? So when you have more than one independent variable. So suppose my x, y, t, theta, suppose these are independent variables, and suppose your u, something people either use u or they use z as a dependent variable. So suppose if you have u as a dependent variable, then this is nothing but dou by u by dou by x. This is nothing but dou by u by dou by y, dou by u by dou by t. All these are called as a partial derivatives. So if you have an equation that involves these partial derivatives, then such equations are called as partial differential equation. So this is the two bifurcations of differential equations. We will be concentrating on the left side, that is ODEs. So let's start with the ODEs. So whenever now I say differential equation, that means I mean ordinary differential equations. Okay, so what are some examples of ordinary differential equations? So if you will see all these 5 examples, they are equations, and since they involve derivatives, we will call them differential equations. Like if you see the first 3 equations, they involve ordinary derivatives, therefore they are called as ordinary differential equation, whereas 4th and 5th example involves partial derivatives, therefore those are the examples of partial differential equations. So this is how any differential equation looks like. Now whenever we study ordinary differential equation, there are 2 things which one should know. What is order of a differential equation and what do you mean by degree of a differential equation. Now let's see order of a differential equation. So it is the highest derivative that occur in a differential equation. Now let's take some examples. So if I take the first example, if you see, it has d cube y upon dx cube. That means this is a third order that is occurring in the differential equation. So what is the order of this differential equation? 3. If I go for the next example, it is x plus y into dy by dx raised to 4. Now here if I expand this, if I do a plus b raised to 4, I will have at the end y raised to 4 into dy by dx raised to 4. Okay, dy by dx raised to 4 is not same as d4y upon dx4. Okay, so even though if I expand this as a 4th power, what I will get is dy by dx only, and therefore order of this differential equation is 1. Now here if you see, what is the order? d2y by dx square, so therefore order is 2. Here if you see, so here 6 is the highest derivative that is occurring in the differential equation, therefore order is 6. And here this is homework, so you have to comment in the comment section and tell me what is the order of this differential equation. Okay, so I hope the concept of order is clear now. Now the next important thing is degree of a differential equation. So what do you mean by a degree of a differential equation? So once you point out the highest derivative, you look at the power of that highest derivative, and the power of that highest derivative is called as a degree of a differential equation. And your differential equation should be free from radicals. Radicals means what? Fractions. Like you should not have raised to 1 by 2, something raised to 3 by 2. If such a thing is there, you first remove those fractions by squaring or by cubing both sides. And once you remove those radicals, and then you see what is the degree. Okay, so in degree you have to make sure the differential equation should not contain any radicals. For order it's okay, but for degree this is the point which one has to take care of. If you see the first example, what is the highest order? Order is 3, right? Because we have d cube y upon dx cube. If you see what is the power of this, the power is nothing but 1. So therefore, this is a degree 1 differential equation. If you go for the second one, if I expand this, what I have y raised to 4 into dy by dx raised to 4. So here the degree is 4. Now here you simply can't say the degree is 3, though here answer is matching with 3. But the first step you have to do is you have to remove this radical. So what I will do is I will square on both the sides. So once I square, I have d2y upon dx square raised to 3 equal to x plus 5 raised to 10. And now there are no fraction. And now this is nothing but what is the power of d2y upon dx square? The power is 3. Therefore this is a third degree differential equation. If you go for the fourth one, here also if I expand this, so highest order is 6, and I will look the power of this, which is nothing but 2, and not the power of dy by dx. Okay, so here the degree is 2. And this is the same as the last example. So in the comment section, please mention the order and degree of the fifth differential equation. Okay, so I hope the concept of order and degree is now clear. So let's go to the last point, which is nothing but solution of an ordinary differential equation. So what do you mean by solution? See, till now you have studied equation like x plus y equal to 4 and x plus y equal to 10. If I want to solve this equation, I simply subtract or whatever, and I will get some values of x and y. So x and y's are what? They are the numbers. Now here the solution are not numbers, they are the functions. Okay, so a function is said to be a solution over an interval if it satisfies the given differential equation. Okay, so once you have some y equal to something, you find its derivative and you plug it into the differential equation. If that differential equation is getting satisfied, that means the function y is the solution of that differential equation, and the graph or the curve of those solution is called as the solution curve. So let's take an example so that the picture will be clear. So if I take, so this is a first order linear. Linear means what? Degree is 1 differential equation, and I want to find what is the solution of this. Now if I take this, what is this? This is a circle. So if I take x square plus y square equal to 1, now there are two ways to verify whether something is a solution or not. Either you differentiate this and get this differential equation, or you find dy by dx from here, substitute in the given equation, and you get LHS equal to RHS. Both the ways are fine. Whichever suits you, you can go by that way. So here if I differentiate, derivative of x square is 2x, derivative of y square is 2y into dy by dx. The chain rule we apply is equal to 0. And when I divide by 2, I get the given differential equation. So here this is the solution of this differential equation. So what is the solution curve? Circle of radius 1 with center origin is the solution curve in this case. Now if you observe, there was nothing special about 1. Right? Even if I take x square plus y square equal to 2, that means the circle of radius root 2, even if I differentiate both sides, I will arrive at the same differential equation. Similarly, there is nothing special about 3 also. So if I replace my right hand side constant by some arbitrary constant c, then all this collection of circles will also form the solution of this differential equation. And therefore, usually for solution we have two categories. One is general solution, one is a particular solution. So what do you mean by general solution? So if you have a solution that involves arbitrary constant, then such a solution is called as a general solution, and the one which does not involve arbitrary constant, then we call them as a particular solution. So like the first one, second one, third one, these are the particular solutions of this differential equation because it does not have any arbitrary constant. Whereas the last one is c. C can be any real number. So since c is an arbitrary constant, we call the last solution as a general solution, whereas the previous solutions as the particular solutions. Like if you want to see, let me show you on GeoGebra so that you can visualize the things. So here if I just write down x square plus y square equal to c, and then this is the slider which I get, and since I know that my circle won't have the radius 0, so let's make the changes here. So for the slider the minimum should be 0 and let's take maximum as 100. Okay, so we are done with the settings. Okay, now as I move my slider, so when my c is 5, I am having the circle of radius root 5, and now if I change the slider, so all these circles I have kept till 100. So all these circles are, and here I have kept from 0 to 100, but here c can be any positive non-negative real number, then those will be the solutions for the given differential equation. Now when we are talking in this framework means now we are talking about the differential equations. So these circles will be called as the solution curve to the differential equation. Which differential equation? X plus y divided by dx equal to 0. So these are the solution curves to that differential equation. So once I fix the c, this becomes a particular solution, and if I am varying the c, then it becomes a general solution. So I hope the solution curve is clear to you. Okay, let's jump back to our presentation. So this is the first example. Second, if I take x minus y divided by dx equal to 0, then one can verify that this forms the solution. And this is a very standard equation which you have seen in your 12th. But those are not seen, not to worry. Here if I make a changes, so what do I have? Here I have y square minus x square equal to c. And now if I change the slider, okay, let me remove the circle. What I get are the hyperbolas. Okay, here I am getting only vertical hyperbolas because I have given the value of c as positive. So now if I give the value of c as negative also, minus 100 to plus 100. Okay, now if I run this, let me close this out. So these are the horizontal hyperbolas which you are getting right now when my c is negative, and as soon as c becomes positive, I get the vertical hyperbolas. So all these things, so all this forms the solution of that given differential equation. All these hyperbolas are called as the solution curve to this differential equation. So the solutions are called as the solution curve of the given differential equations. If all these things are clear, make sure you take this differential equation and verify whether these are solutions or not. Sin x, cos x, sin x plus phi in the last one. And tell me which of them forms a solution, like option 1, 2, 3, 4. Among them, which forms the solution and which do not form the solution. So I hope this session is clear. If you have any doubts, you can comment in the comment section and ask me those doubts. Thank you and have a nice day.